No, but we do talk about division with remainders.
Yes, but that's okay.
But then that's
You
what
don't
they
use
have.
that symbol. That symbol has no meaning. For whole numbers, that division symbol is only meaningful when you know ahead of time you have either partitive division or measurement division.
What
You have to
symbols
know
are we
that.
talking about? Just the division sign? You don't use it. When do we not use it?
I give you two arbitrary numbers. You cannot say that. You cannot say that. Huh?
Don't use blue.
Of course, when I said with the division sign.
Well, or if they're gonna set it as.
Yeah, well, if they're white
Themselves.
that's what they would do.
Right, are they gonna set it in a long division format?
Yeah.
That's what you wrote.
That's the problem. I think that's the problem.
Well, is that so hard for you to understand why you cannot do it?
Differentiate, right. They don't.
Is it so hard for you to understand you cannot say this?
I thought you just said that.
So,
Right.
we see
Do
that
you
all the time.
understand why you cannot say this?
No.
Yeah.
No. What does the English language require? You form a sentence, you can just have a verb, and it has a subject, followed by a verb, by a predicate. That's the sentence structure, right? In principle. In practice, you say, table eats man. That's the correct sentence. Table eats man. There's a subject, there's a verb, there's a predicate. You say it? No, you don't. You exercise common sense. The common sense in mathematics would, in our case, not common sense. It's a matter of definition. This symbol is meaningful only when what? When what? You know ahead of time the first number is the multiple of the second. That's the agreement. Yeah, you can argue about that. So you cannot write it.
So you're saying it should be written the other way if.
No, you just say division of remainder of 27 by 5.
Right, the kids aren't going to do that in the book.
Well, your kids are taught that way. You save them a lot of trouble. You save yourself a lot of trouble. You're doing a good deed for the next generation. Yeah.
I think that it is true that it's so permeated within the elementary culture of this, that in order to do it, you can almost train the kids, so they would like spotting that after a while, I think, which would be the kind of like, well, catch the book or something like that.
Well, of course, after you've taught them correctly, the next grade, they unlearn everything, right? So, but you don't worry about those things. You can, you know. You can do what you can. You can only do what's under your control, and the rest you just leave it to. That's life. Well, but of course, ideally at some point, every teacher becomes knowledgeable enough to do the right thing, then you don't worry about it. But you're not in that era yet. I hope we're heading to that era. Is that up there? Are there other questions?
So you have a huge number, 127.
There you are. You can do better than that. 19972.
Go to 3.
1. Yeah.
Okay.
You want to say, compare that with another number, right? Like
Right.
297.
Sure. And you don't know right now.
Do you dare write this?
That's my question.
No.
So you should, by default, start with.
Take the division of remainder of this by 297.
Okay.
Saying retroactive.
Right. That's what I was. That's what.
It happens to be a multiple. They say, oh yeah, this is a case of actually positive division or measurement division.
But until you know.
And then
Until you know, you can't.
Can't say.
so I have a question that you may not want to answer, but do you know the history behind that symbol?
No, I don't know. Well, I vaguely know. It's certainly nothing before 1400.
Is it kind of like maybe like a fraction, like there's going to be some kind of fraction over some kind of fraction instead of writing?
No. The concept of fraction as a division came later.
Okay.
Definitely came later. There's a history to every one of these symbols. I think you go Google history of symbolic notation. Try that. Wikipedia might have something like that. Yeah, you can try that. Some of the key ones I know, but not in general. The equal sign, for example, that's a long history. That's I think it started about 14 something. Okay, now let's do more about division. I think by popular demand, you want to see something more reasonable, right? Long division, and if nothing, review, right? So I want to begin with a more reasonable division. 8, 79, division of remainder, of 879 by, let's say 6. Let's do that and give an explanation. Now at this stage, obviously we're not going you really want to understand why this thing works. So for us at this point, it doesn't make sense. I assume you know how to do long division. That's why I didn't talk about it. So that's taken for granted. But we're more interested in the interface between the explanation and your mechanical procedure. Okay? So first of all, the mechanical procedure is no question what it is. So then 4 goes into that. That's what it is. Okay?
Yeah.
Now the explanation, of course, now at least you have some sense by now, falls in 2 steps. The first step is you have to capture everything you have done here in symbolic language. This is strictly for everyday consumption, meaning that you have compressed the whole thing into some mechanism, but it's not the mathematical statement. Mathematical statement concerns use of symbol, use of ordinary equal sign, things like that. So we want to capture everything we have done here by a sequence of equations. So the first thing is, what do? We sort of divide 6 into 8 and find out what the portion is, what the remainder is, right? So what you have is that you always begin with the first digit, the leftmost digit of the dividend. What do we call that number? So 8, what you have is that 8 equal to, you divide by 6. What is the quotient? What's the remainder? Well, that's simple. It's always simple. Because you have, by choice, isolated it to be a single digit thing. Right? Just add one digit at a time, so it's always simple. That's the whole point of long division algorithm. I cannot do the complicated task all at once. I break it up into much smaller pieces, right? So that's that. And now you notice, right? Here is, you pull down the 7. And as I said, that pulling down is not a mathematical procedure. What you're saying is, multiply the remainder by 10, add the next digit to it. So that's exactly how you get 27. I think in the book, I actually wrote, instead of write 27, I actually wrote 20 plus 7. Am I right? I think that's what I did. So 27, again, you always divide by 6. Right, so then, you know what it is. 4 times 6 plus 3. Good? Now, I have another remainder, 3. So, the prescription is what? 3 times 10 with the other digit added. So that's 39. So this is a total capturing, mathematical capturing of this weird-looking thing. This is a weird-looking thing. You notice that, right? There's nothing quite like it. It's like a house, and then you have some people wiggling inside, something like that. I never could that make sense. Did you ever try to think about it? That's a weird procedure. That's why the explanation is so beautiful, because out of this you can make sense. Okay, so now we try to make sense. We know that. So what we know is 1, 873. No, 879. Sorry, 879. Nine is equal to Q times 6 plus R. That's what you want. In the back of your mind, you're only marching towards one single goal. That's the goal you're aiming at. All right, so every step, whatever you do, you're asking yourself, am I getting closer to this? If not, don't do it. And if it's not obvious, you try to maneuver yourself in the position of marching towards it. That's all there is to mathematics. At each step, you just say that's what I want to do. All right, so 879. This is ubiquitous. You will have to use it. What do you call it? Expanded form. So that's something you do without thinking. 8 times n squared plus 7 times 10 plus 9. Good. So maybe, yeah. No, I think I better do it. Let me call this equation A, equation B, equation C. How's that? I am tired of 1, 2, 3, like ABC. That can be further than 1 by 1. Okay. So in this case, of course, I arrange things to be so simple that right away you see there's a substitution to be made. Right? You're marching towards this. Now, okay, so you want to think, that's how you think. You like get there. You have all these things. If you can replace every one of them by something of this nature, you just do it. Right now, what is there you can do? Well, look at it. This looks like this one. So that's what you want to do. Therefore, this is 1 times 6 plus 2 times 10 squared. And now, of course, using A. That's an order substitution. Right? Plus 7 times 10. This part okay? Right. Now, of course, I can leave it like this. That's not a problem. But it's just that if you know this is what you want, then you may as well, at every opportunity, give yourself some assurance that you're doing the right thing. Then you might, you don't have to, you might want to rewrite it to make it look like this, and then you feel better. Right? You want to feel better? Right, so we do that. There's always sensible people in this world, right? 5 times 10 squared times 6 plus 2 times 10 squared plus 7 times 10, 5. First of all, never mind what has been done, just check that this indeed is equal to this. You agree? Right. Now, no matter what, the first requirement is that you be correct, right? So this is correct. Now, when it's already correct, then you can ask, why on earth do you do it? Well, it's because exactly, as I said, this begins to look like something like this, and that's a good thing. Is that good? That's it. Can I go on? All right. Now at this point, of course, I'm still single-minded about this thing. Right? What I want is very clear. I want this. Here, this is in place. What about the rest? That's still a mess. I want to reshape them. That's how you think. You know? Educate them. So what can I do? Look around. What are the tools at your disposal? What are the tools? What have you got to use?
27 to 39 somewhere.
That's all you have got to use. That's all you have. Right? These are the raw ingredients. And therefore you want to progress. You draw on your resources and say, does it help? Do they help? Look at this. That. Nothing. But you recognize what? Now this is what, of course, there's some thinking involved. Like that. Look, ask yourself, what is it say? Never mind what the symbols say. What is it? What number is it? 270. It's 270. What does it suggest to you? 27. Right? So you do it. Right? Right? So you don't need to move that, you just concentrate on this. This is 270. 270, of course, is same as this. Correct? And of course I do it, not because I feel like it, but because it helps my cause. Right? So now I'm in business. This calls for another substitution. This is, okay, now reject that amount. That's it. There must be a better way now. But okay. 27 is equal to this. Times 10.
Plus 9.
Oh, sorry. So that's, so I'm using B here. Right, so now again, look at this. It doesn't look very tidy. And the reason you want it to look tidy is that if it's not tidy, it obstructs thinking. So you want to make it look tidy. You want to make it look like something like this. Right? If that's what you want, you should display the 6 prominently. That's all there is to it. So 4 times 10, 6. All right? That's equals 10, 9. Okay? So now, again, with in mind the fact that this is where you are heading, then it's clear you can do better. Don't forget, that's what you want. And this tells you you can do better. So then again, anyway, in any case, there should be condition reflex. Times 6, times 6, every time you see that happens, it's distributed. So therefore it's 1 times 10 squared plus 4 times 10 times 6. Right? Not yet. Alright? So we got that straightened out. this part now. Again, you ask yourself, what are you going to do with this? And you remind yourself, I want to do only one thing, which is to go this. Therefore, and you say, oh. Therefore, I rewrite it to make it look plausible. Indeed, it looks plausible. Now I bring that up. 6 times 6. No, sorry, what 6 times? Oh yeah, 6 times 6, yeah. Plus 3. Now that's your final destination because this, everything, every ingredient is already here. So you do exactly the same thing as before, tidying things up, right? 6 should be displayed correctly. So now finally this becomes 1 times 10 squared plus 4 times 10 plus 6 times 6 plus 3. And I purposely display it without saying this is 146. Of course it's 146. That's the advantage. You see it, right? But in this form, you understand the fundamental issue, fundamental conception of our standard algorithms. As I said, it's 1 digit at a time. It tells you that's exactly how we got those 1 digit at a time. Yeah. Right? So now that you're inspired, are you?
Yeah. No, really, it is.
Why don't you do something? All 59 by 7.